Hello everybody, today I will give an introduction on frequency response techniques in feedback control systems. As you may know, I publish my lecture notes in my GitHub repository, which is here, okay? And normally, I cover frequency response techniques in my lecture notes starting from lecture 14, 15, 16, 17, I think, until 18 and 19. Okay. However, due to this extreme situation that we are dealing with, what I did is I get 14, 15, and 16 lecture notes, and I simplified it to obtain a new lecture note, which I call it frf.pdf in these notes. Okay, so what I do is I technically try to simplify and refine Nyquist plot and Nyquist analysis to make it easier to handle using technical distance education. And technical Nyquist plot is one of the hardest things in this class, and I try to make it easier for you. Okay, so what is a frequency response technique? And today's topic will concentrate on polar plot, which is the fundamental part of the Nyquist plot that we will analyze. Okay, so from your signals and systems courses, and I think partially from your circuit 2 course, you know something about frequency response. We assume that we have an LTI system, which is the most important assumption. In that case, we have a frequency separation rule. So what does it mean? Let's assume that our input is a complex periodic signal. Okay, it doesn't have to be complex, but it makes the analysis easier. And if we wait enough, as t is going to infinity, or we wait enough such that transient dies, and we assume that the system is stable, then what happens is, at the steady state, output will look like m times e to power j omega t plus some phase. Okay, and it's something like this. Okay, so and here m is real, it doesn't have to be real, and phase is an angle, let's say between minus pi to pi. Okay, how we can find m and phase, and we covered this previously in signal and system course. So under the assumption the system is LTI, y steady state is equal to g j omega times e to power j omega t, and proof is relatively easy. Okay, g j omega is a complex signal, and from this perspective we can compute m as the magnitude of g of j omega, and phase is equal to simply the phase of g of j omega, and omega is the same frequency with the input. Okay, the idea is very simple, and we can think it as an experiment. We apply a sinusoidal input to the system. We look at the magnitude scale m, and we look at the phase shift. And if we do this for each of the possible frequencies, or many frequencies, we can characterize the frequency response of the system, which can be helpful for designing controllers, filters, or doing a different kind of stability or robustness analysis. Okay, so how we can plot frequency response? I think most of you know the Bode plot, and we will cover that again. Okay, but not in this course, later. But today we will start with the polar plot. Okay, so what's a polar plot? Okay, in a polar plot, the basic idea is we try to map the j omega axis. Okay, what is j omega axis? Is simply j omega, and omega, let's say like this, omega is an element of r plus, so we do it for positive real numbers, and we use the g of j omega, and we try to plot it on a new complex plane. Actually, the process is very easy. Okay, so we start with omega is equal to 0. Okay, we pick a different frequency here, different frequency here, different frequency here, different, and we go until omega is going to infinity. So what we do? Let's start with omega 0. Okay, we compute g of j 0, and we look at where it locates on the polar plot. Let's assume that it's here. Okay, we look at the next frequency. Let's assume that this is g of j1. Okay, we look at its mapping here. We do the same thing for all of the frequencies. This, okay, or let's make it colorful. Okay, and let's assume that when omega is going to infinity, g of j omega is going to 0, which is a very common thing. Okay, and finally, if we do this for all of the omegas, of course there's infinite many of them, and if we plot them like this, it is our polar plot. And similar to our j omega axis, polar plot also has a direction, and direction is important for analysis and other kind of purposes. Okay, the idea is very simple. It's similar to water plot, but the main thing is here everything is in Cartesian scale, so there is no logarithm. And the other thing is we lose frequency information if we don't label specific points, such as omega is going to infinity, omega is going to 0. But we don't lose the direction. Okay, let's start with simple examples. G1 of s is equal to s, G2 of s is equal to 1 over s. If we replace it s with j omega, we obtain j omega here, and I think here it will be 1 over j omega. It is equal to minus 1 over omega times j. Okay, which is good. This is very simple because what we do is we map the positive imaginary axis to positive imaginary axis. So it is technically an identity. So this is our mapping. Okay, and this is g of s is equal to s. But here we have a similar but a different mapping. Okay, first of all, real part is always equal to 0. So it will be on the imaginary axis. Since omega is greater than or equal to 0, it is always located in the negative part of the imaginary axis. Okay, so we will cover this region. Okay, now let's look at the direction. When omega is equal to or equal to 0, g2 j omega is going to a minus infinity j. So we will be here. Okay, so in this direction, omega is going to 0. So we are coming from negative infinity. Okay, and when omega is going to infinity, g2 of j omega is going to 0 because of this. So at infinity, we will be here. Okay, so in this part, omega is equal to 0. Now, origin is infinity. Okay, so it's very simple. So they look similar, as you can see, but they are categorically different. One is a differentiator, other one is an integrator. One is a high-pass filter, other one is a low-pass filter. And it technically covered in this polar plot structure. And if you look at the illustrated drawing, we can see that the structure is very similar, and it's nice. Okay, so if you remember, I post every figures and every detail in my lecture notes. Okay, this is more of a guidance. You can always look at my lecture notes. Let's start something different. Okay, g2 of s is equal to 2 plus 1 over s. Okay, so we already plotted 1 over s in the polar plot. So what happens if we add 2? So first, let's write the complex plane for j omega equation. It is equal to 2 minus 1 over omega times j. And if you remember, we already plotted this, which is here. Okay. So here, the equation says that you need to add 2, and 2 is a real number. Okay. So what we need to do is for each frequency here, okay, let's say we have 0, we need to find, normally it's here, but we shift it by 2 to obtain this. If you do the same thing here, Same thing here. It goes like this. And our final plot is simply this. Okay? No, sorry. Okay, it's a mistake. It should be here. Okay. We technically shift everything to the right in the real axis. Okay. Adding a real number shifts things on the real axis. If we add a complex number, which can come with other things, what we need to do is we need to shift it in the image axis. And adding a real number is very common. For example, in a PD control, P action is a real number. Okay, and technically this is a PI controller. And here, okay, we already wrote it. No, I didn't. Okay, this is a polar plot of a PI controller. Polar plot. Okay, so let's change it, and now we have a PID control, right? Because this is the D action, this is I action, this is P action, and let's look at the polar plot. So what we need to do is S is going to J omega. Okay, if we do the replacement, we obtain this simple behavior. Okay, this is the imaginary part, and this is the real part. Okay, so real part is always at 2. Okay, it is shift. Let's concentrate on this part first. Let's draw it, then we can go to the real part again. Okay, if we ignore 2, let's ignore it like this. Okay, we don't see it. This is always complex, right? So in the complex plane. So is it positive or negative? As you can see, depending on the value of omega, it can be both positive and negative. Because if omega squared is greater than 1, it is positive. If omega squared is less than 1, it is negative. Okay. And indeed, if you look at it with more detail, when omega is going to 0, what's happening to the g of j omega? Okay, it's going to 0. It is going to minus infinity j. Okay. When omega is going to infinity, g of j omega is going to, where? This will dominate the behavior, infinity j. So this polar plot technically covers the whole imaginary axis. Of course, if we ignore the 2. Okay, so let's do it. And if we look at this, the direction is like this. Okay, in this direction, omega is going to 0. In this direction, omega is going to infinity. Okay, let's try to find this point. Okay, so when g of j omega is equal to 1. Okay, in this case, of course, 1, no, sorry, it is wrong, 0 times j. So omega square minus 1 divided by omega should be equal to 0. So this is equal to 1, omega is equal to 1. Okay, so here omega is equal to 1 radian per second. Okay, so now let's not ignore 2. So what we do is we shift everything by 2. So our original polar plot will be like this. Okay, so let's change the color. So here, okay, like this. Instruction. And this is the polar plot of G what? If S is equal to S plus 1 over S plus 2. A PID controller. A PID controller will always have this kind of polar plot. Okay, there will be a real part. It will be a line intersecting positive real axis. This is technically the P action. Okay, and here this is the I action. This is the D action. Okay, and as you can see, integrator and differentiator are affecting different frequencies because of their high pass and low pass structure. Okay, so if we look at all of the polar plots that we draw so far, we have S, 1 over S. So this is at D, this is I, this is PI, and this is PID. Okay, these are polar plots. So these are the most simple and basic polar plots, and obviously we will draw more complex and more important polar plots to analyze system behavior. Okay. what it is. For example, let's start with a low pass filter. Okay, 1 over s plus 1. So what do you do? S goes to j omega, so g of j omega is equal to 1 over j omega plus 1. Okay, this is good. So what we can do is we can technically make it easier to understand. Minus j omega plus 1 here, if we multiply the conjugate, omega squared plus 1. Okay, in this case the real part will be omega squared plus 1, if I'm not making any mistakes, omega squared plus 1 times j. Okay, so this is the real part and this is the imaginary part. Okay, so if you would like to find the magnitude of g of j omega, taking polar coordinates, it's equal to simply 1 over square root of omega squared plus 1. If we look at the phase, okay, it is, I think, a tan minus omega. Okay, so normally the phase of this is equal to a tan omega. It's in the bottom, we just change it in the upwards. Okay, so let's check if they're correct. They're correct, everything's nice. Okay, so this is the real part and this is the imaginary part. Okay, let's analyze this. Okay, the important thing is, the most important thing is when we cross the real and imaginary axis. Okay, so in which quadrant, in which frequencies you are located. The fine details, the exact shapes and curvatures are somewhat secondary. It's not very critical for this course, especially if you are drawing by hand. Okay, let's look at the real part. As you can see, since omega is greater than equal to 0, real part is what? Greater than equal to 0. Technically, it is always greater than 0. Okay, and imaginary part, as you can see, is always less than 0 because of this minus. In this perspective, technically, what we can do is, let's use this and change the color to something ugly. So these are not in my whole plot. Everything is in this quadrant here. Okay, so let's start with omega is equal to 0. Okay, omega is equal to 0. What's the real part? Is equal to 1, right? Okay, what's the imaginary part? It's equal to 0. It's good. Okay, it is here. Okay, very good. So what we can do is we can look at omega is going to infinity. Where we go, real part will go to 0. If you look at this, you can see that. Imaginary part will go to 0. Okay, so we will be here. Okay, this is omega is equal to 0. This is omega is going to infinity. So what we can do is we can just draw arbitrary things. Okay, but the good thing about root locus, Nyquist, and other kind of things that we draw in this class is we generally obtain smooth graphs because these functions are simple and they're technically smooth if you don't cross a pole or 0 in J of x. Okay, so my guess is it is, let's clean this. Okay, and change the color. My guess is it is something like this. It's kind of easy to see that because if I increase omega, if you look at the real part, okay, if omega increases, what's happening to the real part? Real part is monotonically decreasing, right? Which is fine because this is in this projection. What's happening to the imaginary axis is, let's look at this. If I increase omega, initially omega starts from 0 and this is close to 1. Okay, so omega squared plus 1. It will increase in magnitude a little bit initially, and later it will decrease and we will have this structure. Okay, so let's pick a specific point and I will clean some parts because they're not very critical. I will see them later. Okay, So let's pick omega is equal to real part is equal to what? 1/2. Imaginary part is equal to minus 1/2. Okay, so when we are here, it is 0.5. We are here. Okay, so sorry for this. 0.5, and this is the middle point. Technically, this is an ideal circle, but half circle, of course, it's not very important. The idea is obtaining this qualitative structure in this course. Okay, so if you look at this, we have the same thing, and okay, so our assumptions and computations are all correct, and this is a good polar plot of 1/s+1. Okay, let's change the transfer function a little bit. Put an s in the above transfer function. So what we will do is, let's try it and compute j omega. Okay, we have j omega plus 1. Okay, j omega times 1 minus j omega squared plus 1. Okay, so if we look at this in detail, it is j omega plus, I guess, okay, because j squared is minus 1, omega squared divided by omega squared plus 1. So it is equal to, I think, omega squared plus 1 plus omega squared plus 1 j. This is the real part, and this is the imaginary part. Okay, so let me check for my computations. Yes, everything's correct. Okay, so we already computed this. This is correct. If you look at the magnitude, it's obvious it's equal to this. And if you look at the phase, this is equal to arctangent 1/omega. Okay, so let's analyze it in a similar framework. This is the real part. This is the imaginary part. As we can see, real part is always greater than 0. It's the same thing. In this case, imaginary part is always greater than or equal to 0. Okay, so if we eliminate other regions, our polar plot will be included in this region. Okay, so let's start with omega is equal to 0, because it's one of the most important frequencies, because it's the DC frequency. Real part is equal to what? 0. Okay. Imaginary part is equal to 0. It's good. So we are starting from origin now, which is not very common. Because in high pass filter, we are having this kind of behavior. And this is omega is equal to a0. It's nice. Let's look at infinity. Omega is going to infinity. Real part is going to 1. Okay, because of this. Imaginary part is going to 0 because of this. Okay, so we will be here when omega is going to infinity. We follow the same logic. And let's change the color. Okay, my polar plot should be something like this in this direction. And if you look at the magnitudes, you will see that it's true. Let's try omega is equal to 1. Okay, real part is equal to 1/2. Imaginary part is equal to 1/2. So we will be here. This is 0.5. This is 0.5j, and this is equal to omega equal to 1. As you can see, if I add s, I just flip the polar plot with respect to the real axis. And if you look at both polar plots, we can see the answer here. Okay, and this. They're very similar in shape, but one of them is always located in the negative part of the imaginary axis. One of them is always located in the positive part of the log axis. So this is more like a phase leg transfer function. This is more like a phase lead transfer function, which we'll cover later. Now let's change the gears and increase the order of the transfer function and go to higher order systems such as the second order transfer function. Okay, g of s is equal to 1 over s plus 1 square. So what's the process? Everything is same. Only the computations will be a little bit messier. Okay, g of j omega is equal to 1 over j omega plus 1 square. Okay, if we do the same tricks, we can see that, okay, this is equal to what? Okay, so we do that, okay, this will be omega square plus 1 square, because n, this is minus j omega plus 1 square. Okay, so let's analyze it a little bit more, and if we look at this behavior, one in here, we can see that this is equal to 1 minus omega square divided by omega square plus 1 square, is the real part, minus 2 omega divided by omega square plus 1 square times j. Okay, so this is my real part, and this is my imaginary part. Okay, let's check if my computations or intuitions are correct. They're right. Okay, it's slightly different than the other one. Okay, now this is more complicated because let's look at the imaginary part. Imaginary part. Okay, since omega is greater than or equal to 0, this is always greater than 0. It's nice. We have minus. Okay, it's always less than or equal to 0. So in this case, we eliminate this region. Okay, this is good. So imaginary part is always greater than 0. Okay, let's say imaginary, let's say real for all frequencies. Okay, good. But let's look at this. As you can see, depending on value of omega, and the crossing point is equal to 1, real part can be both positive and negative, and this is negative, this is negative. So when omega is less than, and this is omega equal to 0, or is between 0 and 1, this is what? Real part is positive, right? Because omega is small. 1 minus omega square is greater than 0. And when we pass this threshold, it becomes negative. So my transfer function will be somewhere, or my polar somewhere here. Okay, so let's clean everything. Okay, let's compute the mapping of or the polar plot locations at specific frequencies. Let's start with omega equal to 0 here. Okay, omega is equal to 0. If we look at the imaginary part, it is equal to 0, which is good. If we look at the real part, it's equal to 1 minus 0, 0 plus 1 square, so it's equal to 1. Okay, so we start with 1. This is 1, and here omega is equal to 0. Okay, the second important point is the crossing of the imaginary axis, which is omega is equal to 1. Okay, so if we compute the imaginary axis, it is equal to minus 2 plus, okay, 1 square plus 1 square. I think it is equal to minus 2 over 4 minus 1 over 2. So in this case, we are somewhere, okay, let's make it a little bit larger here. Okay, here omega is equal to 1, and this point corresponds to, let's say, 0.5j. Of course, we have minus. Okay, oop, what's happening? We have minus. And if we draw the polar plot in between, we can have something like this. It goes in this direction. Now, let's clean this and to have some space because we have computed it. Omega is going to infinity. What's happening is imaginary part is going to 0, real part is also going to 0. Okay. An important thing is if you look at the g of s, it is a low pass filter, so as omega is increasing, magnitude is decreasing, and it's monotonically decreasing. And if you look at the magnitude of g of j omega, I think it is omega squared plus 1. Okay, square root of one of them. So 3 divided 2. Okay, so it is fair to assume that my polar plot will be something like this. Indeed, we can also compute, and here omega is going to infinity, angle of arrival by computing the phase angle when omega is going to infinity. So if you look at the behavior, we can fairly easily see that this will be approximately equal to 1, this will be going to 0, so technically real part will dominate the behavior and it will be minus pi. But it's really not important, it's important just to have this kind of behavior. And this is my polar plot. Okay, so let's look if it's correct. I think it should be correct. Yes, it's correct. Every detail is here. Okay, as I told you before, the important points are the crossings of imaginary and real axis, and of course, crossing of the origin. In between, the good idea is just obtaining the behavior qualitatively, not exactly or quantitatively. Okay, so this is a nice, good polar plot. Okay, now we can clear this. Okay, now let's go and test a different transfer function, which is a little bit more complicated than the previous one, of course. Now we have a third order transfer function. Okay, so let's do the same thing. G of j omega is equal to 1 over j omega plus 1 cube, okay, minus j omega plus 1 cube divided by omega squared plus 1 cube, okay, and if we compute everything, we will obtain this omega squared plus 1 cube. That's the real part, and the imaginary part will be omega cube. Sorry for that. Okay, this is a brute force computation. 3 omega divided by omega squared plus 1 cube times j. This is the real part, and this is the imaginary part. Let's see if it's correct. Yes, it's correct. Okay, this is right. Now, as I told you before, the important thing is understand the crossing of the real and imaginary axis. Okay, and of course, when omega is good. So we start with, let's say this is real, this is imaginary. Okay, when omega is equal to 0, and this is the real part, this is the real part, this is the imaginary part. Okay, this is omega is equal to 0, it's the starting point, and of course we will go to infinity. So when real part changes its direction or sign, when 1 minus 3 omega squared is equal to 1, it happens when 3 omega squared is equal to 1, omega squared is equal to 1 over 3, omega is equal to square root of 1 over 3. Okay, so our second important point is 1 over 3. Okay, this is good. And this is the change of the real axis. So what happens to the real part in this direction? Let's see that. Okay, when omega is small, real part is positive, which is good. Okay, this is positive. When omega is larger than this corner, or like say critical frequency, it becomes negative. Okay, this is good. Now let's look at the imaginary axis, and imaginary part. And imaginary part changes its direction when here omega cube minus 3 omega is equal to 0. Of course, it happens when omega is equal to 0, which is not very important. And omega squared minus 3 is equal to 0. omega square is equal to 3, omega is equal to square root of 3. Okay, square root of 3. And here, real part is still negative. So when omega is less than square root of 3, what happens is, this is small and this is large, so imaginary axis is indeed negative. Okay, negative. And after we pass this frequency, imaginary part becomes positive. Okay, so it's good. Oh, sorry about that. Now we can draw everything with more detail. Okay, so let's start with omega is equal to 0. The real part is equal to 1. Okay, it's good, it's 1. Let's pick it here, 1. Omega is equal to 0. Imaginary part is equal to 0. Okay, I already did this. Omega is equal to 1 over square root of 3. And we know that real part is changing its direction, so it is on the imaginary axis. So what happens to imaginary part is equal to, okay, omega cube, okay, omega cube. Okay, so it's kind of tricky. No, it's not tricky. So what happens is 1 over square root of 3 square minus 3 times 1 over square root of 3 divided by 1 over 3 plus 1 cube. If we do all of the computations, which is kind of ugly, but we will have something like this. 0.65. Okay, so here we will cross this. Okay. Again, even the exact location is not very critical. Here omega is equal to 1 over square root of 3, and this is approximately 0.65J. Okay, and we have a polar plot something like this. Okay, so let's clean this. Okay, and if we compute everything at omega is equal to square root of 3, okay, we already know that imaginary part will be equal to 0. Okay, so it's under the plot. And real part, if you do the computation, which is slightly easier because it's equal to 1 minus 3. What is omega squared? It is 3. I think it's correct. Right, okay, omega squared is equal to 3 plus 1 cube, and it's equal to x minus 1 over 4, which is easier. Okay, it will be somewhere here. Okay, this is minus 1 over 4, and omega is equal to square root of 3. And finally, if you look at when omega is going to infinity, we will see that both imaginary part and real part will be equal to 0. And indeed, okay, it will approach from pi over 2 angles, and it can see it from the phase computation. Okay, so if we compute the phase, when omega is going to infinity, we will see that, let's make this going to 0, is going to pi over 2. So we will have a polar plot like this. Okay, let's look at the final result. No, everything is fine. Okay, so this is a basic polar plot that we draw here. Okay, so the important points are omega is equal to 0, omega is going to infinity. Okay, the crossings of the imaginary axis and real axis. Okay,